Don't admit to any crimes. Okay. So, does somebody want to give their take on how the test went? Was it better or worse than expectations? How do y'all feel? Better than expected? Okay. Okay. Yeah, I was especially FRQ. Okay. That's good to hear. Yeah, because the FRQ is definitely the scariest part, I think. Uh and the FRQ will be more difficult on the coming exams. So I think exam two is pretty fair game. Usually three is pretty difficult. Uh so yeah, that's good to hear. Before we get started on material today, is there any questions that y'all had from the exam? Like any problems you're not sure about? Well, for those of you who don't know, as soon as Lake is back in town and available, go to her office hours, talk to her about what you missed. It's definitely worth it. Okay. I'm gonna start sharing my screen. Can y'all see? Yes, okay, thank you. All right, so today's week in review, we have a few topics. Let's see. Yeah, so today we're going to be talking about postfix, basically what it is, and some simple algorithms for converting to and from postfix. We're going to be talking about linked lists, the different types of linked lists. This is going to be coming up on PA3. And then we're going to briefly talk about recursion. So let's see. Postfix notation. So I'm not going to do all of postfix notation today because I think to really understand postfix notation, you have to understand trees. And to the best of my knowledge, y'all haven't like learned about tree traversal quite yet. But I'm going to show you the like rudimentary algorithms that you would need to be able to go to and from postfix. So when we're used to seeing like math equations, humans interpret math equations in infix notation, which looks like this, right? Like, as in you evaluate everything in the order that it appears in the equation, right? So 3 plus 4, 3 times 4 plus 2, and we have an order of precedent for the operators. This is all basic stuff. This is what we're used to. This is what a computer is going to understand when a computer is evaluating an equation, usually. So when a computer is looking at an equation, usually it's fed in some kind of order that doesn't really immediately make sense to a human. So in this case, these are all the same equations from before, they're just in a different order. I guess important points from this slide, sometimes this is called Polis notation. If y'all have done leet code, this is like I think 40 something reverse Polish notation. Maybe go check that out. Okay, so converting to postfix notation. So right here is a little table. It's kind of like reverse PEMDAS essentially. Like when you have an infix expression and you're converting to a postfix expression, you give order of precedence backwards. This table kind of, I think it's from the textbook. It doesn't really explain very clearly what's happening here, but essentially the lower the number, the higher the priority. So again, it's kind of confusing. Don't get wrapped up in it. Okay, so rules on the algorithmic approach. This is like 10-point font. I'm not reading that. So essentially, I'm going to let's see. I'm going to walk through the steps that you would need to take to convert from infix to postfix. So this algorithm requires a stack and it also requires a queue. And specifically, this queue is going to be storing our postfix conversion. So this is going to be the actual complete postfix equation. And then the stack will store operators. That way we can preserve the order of precedence. So the first thing that we're going to do is we're going to start reading left to right from this infix equation, and then depending on the precedence of the operators, we either put them in the queue or the stack, and that'll be clear as we move forward. So we start looking at this A right here. If it's an operand, we immediately push it to the queue. So A gets pushed to the queue. If it's an operator, we compare it to the stack. So at the moment, the multiplication operator has higher precedence than this end token. So we're going to push this multiplication operator to the stack. Next thing we get is an operand, which is a B, so immediately to the queue. And that'll go here. And then now this is an example where we have an operator of higher precedence than what this is. So, I mean, I'm sorry if I misspoke before. Let's see. I think the end token has the highest precedence. Yeah, okay, 0. Okay, my bad, sorry, y'all. So specifically in this example, plus has higher precedence than multiplication because it's like reverse PEMDAS. So in that case, we pop from the stack, put it on the queue, and then whatever has the higher precedence replaces it on the stack. So you'll see that happens here. So now we put the multiplication in our postfix queue, and we have the addition operator left on the stack. Parentheses operation basically just resets the order of operations. So as we keep going, you can see C goes to the queue, minus has a higher precedence than parentheses. So minus goes on top, and then D, and then division, E, so on and so forth. So I think this algorithm is kind of confusing if you don't understand trees. So, oh, and by the way, at the end, you just basically empty the stack onto the queue. So I think this algorithm is a little bit confusing if you don't understand expression trees. So bear with me. I'm sorry that I'm rushing through it. I'm going to slow down in a second. So let's see. Evaluating postfix expressions. This one is a lot more manageable, I think. Evaluating postfix is definitely a lot easier than going from infix to postfix. Going from postfix to infix, I think, is a lot easier. So in the example before, we were working only with letters, and we're going to take this same exact equation, and we're going to plug numeric values into those letters. So A is 5, so on and so forth. So now we've got this equation. And essentially to evaluate postfix notation, we again read from left to right, and every time we encounter an operator, we perform that operator on the previous two numeric values and then push that numeric value to this part of the equation. So as you can see, as we would read this, we would have 5 times -2, which is -10. And then we would keep reading, pushing to the stack, reading and reading. And then we have a division here, so we apply that to the first two operators on the stack. So it'd be 40 divided by 8, and that's 5. And then see, -7 minus 5 is -12, and then -10 plus -12 is -22. So I can just do that off the top of my head. This will be a potential test question that you're going to see on future exams. So you probably don't need to be like fluent in postfix to be successful, but definitely understand how to do this on paper. So I'm going to walk through the steps again. So first thing we do is we push tokens onto the stack. So you can see we're going to push 2 numeric tokens, and then when we encounter an operator, we apply that operator to the tokens that were on the stack. As you can see, we had -2 and 5. We apply the operator, and then we keep pushing. So we see another operand. Keep pushing those operands, push 8, and then now you see operators, so 40 divided by 8, which is going to give us 5, and then it's going to be -7 minus 5, which is -12, and then -12 plus -10 is -22. So that's infix to postfix. I would like for this to make more sense. I think to really understand what's happening, you need to understand the concept of an expression tree. So we haven't really talked about recursion yet. And you kind of need to understand recursion to understand why postfix and infix actually make any sense at all. Specifically, when we're looking at an equation, like postfix and infix notation are different ways of describing the same structure. So technically, an equation is like a tree. So when you're learning in class, like the different data structures like queues and lists and whatnot and trees, an implementation of a tree is representing an equation. And you can see in this example, an expression tree is going to have leaf nodes that are operands. So all the leaf nodes of this tree are going to be operands, numeric values, and then all of the parent nodes are going to be actual operations. And as you can see, you apply the operations to the leaf nodes and then work your way up, right? So you've got 5 times 4, just 20, and you've got 20 divided by 2, which is 10, 100 minus 10 is 90, and then 20 plus 90 is 110. So did I mess that up? No, I don't think I did mess it. Yeah. It says output is 100. 110. Yeah, so that is correct. So this is just a basic Geeks for Geeks article. And essentially, the reason I'm showing you all this is because the way that you traverse this tree will give you your output notation. So Infix notation is literally if you were to flatten this tree and read it from left to right. So for instance, Infix notation, you're going to just take all of these nodes and read them left to right. So 5 times 4 plus 100 minus 20 divided by 2. That is Infix notation. And to read the same expression tree as postfix notation, you would do a post-order traversal. So these things line up. So in-order traversal is what I just described, gives you infix notation. Post-order traversal gives you postfix notation. But I don't think y'all have learned that. So this is just a little appetizer. Don't worry if you don't completely understand postfix and fix notation yet, because as soon as you learn about recursion and expression trees, this is going to get a whole lot easier. I completely promise. And specifically, my own strategy for solving the infix postfix problems is if you can get to this tree, then you can get all 3 notations just like very quickly. Okay, so again, sorry to introduce a topic that I think is a little bit too advanced, but let's continue to move on. So next topic is going to be vectors versus linked lists. So we have absolutely beat vectors into the ground. You should know everything that there is to know about vectors at this point. And it's realistically not much. A vector is just an array. That array grows when it needs to. It's continuous in memory. Removing and inserting an element is expensive because you have to increment. You have to shift a bunch of elements over, and then accessing the ith element is very fast because we have random access iterators. The new thing that we're introducing in this class is the linked list. So a linked list kind of balances some of the trade-offs that you get from vector. So there's unbounded capacity, which means you never need to reallocate space for your data structure. Elements are randomly arranged in the heap, so you don't have to have everything right next to each other. Removing and inserting are significantly less expensive, and then accessing an element is significantly more expensive. So there are a few different flavors of linked lists. This one right here is a singly linked list in which your structure, each data member just points to the next data member, which points to the next data member. It's convention in linked lists to have a node called head and a node called tail. Specifically in this example, we don't have nodes, we just have pointers. So we've got a pointer to head and a pointer to tail. And if we wanted to find, for instance, this node, we have to start at head and then actually traverse our way all the way to this node. Doubly linked lists are a similar idea, but instead they're bidirectional. So here we can iterate through this data structure using a unidirectional iterator. So as in, like, if we have a pointer to this node 7, we can find to node 5, we can find node 7, and then we can find node 9, and so on and so forth. But given node 9, we can't go backwards, and we can't go backwards. A doubly linked list solves that issue. So basically it's a bidirectional iterator where you can go forwards in the container, you can go backwards in the container, so on and so forth between these 2 pointers. And what's very remarkable about a linked list is the fact that you don't know where these things are being stored. So whereas a vector has to be stored in contiguous memory, as in, like, each address is directly adjacent to each other address, a linked list is a total mess. So this might be the last index in your hard drive, and this might be the first index in your hard drive. You have no idea. You're basically randomly taking these massive leaps around your memory from one location to the next, right? So if you've got your head node starting here, then you can point to the next place in memory. You can point to the next place in memory from here, but you can't calculate these things. There's no rhyme or reason to it whatsoever. So drawing it out, this is, again, just a little representation of what a single node is going to look like in a linked list. So if you've got a singly linked list, you've got a value and one pointer to the next element, and then a doubly linked list, you're going to have a value and two pointers. I will say the reason that you would use a single list over a doubly linked list is because, as you can see, to store one element in a doubly linked list, you need twice as many pointers, which takes up more memory. It's less efficient. So drawing it out, again, you're going to see something that looks like this. Sentinel nodes. So yes, it's convention to, instead of just having like a pointer to 5 and a pointer to 0 saying head and tail, it's good practice to have an actual node that's initialized like the other nodes, except for it has no value and it just serves to begin and end the list. Those are usually referred to as head and tail, or you might see header and trailer. And these are fixed. So these are fixed in memory. They're statically allocated, whereas these nodes that you see here are dynamically allocated, right? Because who knows how many nodes you need to have in your linked list, right? You might need to have 100 nodes. You might need to have 200 nodes. Because you don't know how many nodes you need to have in your linked list, these are going to be allocated dynamically, whereas the head and the tail will always be 2, so you can go ahead and put those on a stack instead of the heap. As you can see, the example now includes our head and our tail nodes. As you can see, they're written as squares, I guess, to denote that these are on stack memory and these are on heap memory. To delete a node, it's kind of like a little dance you have to do. You can't just destroy 7, because to maintain the structure of this data structure, you have to have 2 now point to next, and 9 point to previous. So the first thing you do is you set 2 next pointing to 2 next, and then same thing with previous. And then now that you've repaired the linked list so that you can still traverse, this node is essentially detached from the list and you can destroy it. It would be a mistake to just take out 7 right away, because now you've lost the information of how to get from 2 to 9. Y'all are going to see this in PA3, and potentially you're going to have a segmentation fault here, because if 2 is pointing to a node that has been destroyed and you try to access that node, that's going to be a segmentation fault, because the pointer is now pointing to invalid memory. So y'all are going to understand this very clearly at the end of PA3. So if you're inserting a node, again, similar thing, you basically have to connect it to the rest of the list. So you'll have 2 point to 7 and 9 point to 7 and then 7 point back. As you can see, it's just a little dance that happens, and then boom, it's inserted. This is significantly less expensive than inserting in a vector, because as you can see, for a doubly linked list, instead of O of n operations to do an insert, it's just 4, so it'll be constant time. And then to empty a linked list, you just essentially forget everything that was in there. So head points to tail and tail points to head. And now it's an empty linked list. Usually in a linked list, the size, or I guess capacity of the linked list is going to be measured by how many times do you have to iterate to get from head to tail. And as you can see, if you set head pointing to tail and tail pointing to head, that size is going to be 0. We already saw this slide. Okay, so a linked list can be the concrete implementation of an abstract data type. So y'all have learned about a stack and a queue. A stack can be implemented with a vector. It could also be implemented with a linked list. The only difference between the two being like the actual underlying mechanism with which the abstract data type is implemented, but the properties of the stack are the exact same. So for instance, you have to push to the head and you have to pop from the head. And it's still O of 1 insert. See, for queues, it's a similar idea between like linked list and vector. The only difference being how it's actually implemented. The properties are all the same. So you push to the tail and pop from the head, just like a queue. Okay, so that's it for linked lists. I think linked lists are usually pretty tame, like as far as understanding goes. Maybe the insert and the erase might be a little bit difficult. If you get stuck during PA3, piece of paper will be your best friend. Okay, recursion. So this is kind of classically known to be like one of the scariest areas of computer science. So I'm going to take it relatively slow. Trust me, it's not that bad. Today, we're not going to be talking about time complexity or how to prove the time complexity of these functions. We're just going to be like giving you a basic overview. So what is recursion? Well, any type of recursive definition is a definition that references itself. So if someone asked me, what is recursion? And I replied with recursion is recursion, I have given you a circular definition, which is essentially what we're doing on purpose. As you can see this excerpt right here, we define a function called factorial, and the return type of that factorial is just another call to itself. So a recursive definition can be broken down into two distinct parts. There's the part that is circular and loops forever and ever and ever, calling itself. And then there's the part that is the end case once you've reached the point at which you stop the cycle. So specifically, there are certain algorithms that can be implemented recursively. This one is the factorial algorithm. Right? Like in mathematics, classically, a factorial is going to be represented as n times n minus 1 times n minus 2. And that's the circular part of the recursion. And then the based case is going to be when we reach the end, which is 0. And then we start returning. So if we look at this code more closely, we can see we've got a factorial function where we take an input in. In this case, we're going to start with factorial 6. We define our base case to be if n is 0, then we return 1. Otherwise, we return n times, and then we call that function on the next lower number. So if we call factorial 6, it's gonna return 6 times factorial 5, and we evaluate factorial 5 to be 5 times factorial 4, and so on and so forth until we reach 1 times factorial 0, and then factorial 0 will just return 1. And then essentially we've written a definition where we have 1 times 2 times 3 times 4 times 5 times 6, all the way back up, and then we get our answer. A recursive proof. So this is something that you might see in 222. Essentially, to prove that this works, you first have to define your base case. So in this instance, 0 factorial is 1, which is where we're going to end our recursion. Our recursive step is just the next higher order factorial. And under the assumption that P of k gives you factorial of k, then we can prove that factorial of k plus 1 is going to call factorial of k, multiply it by k plus 1. And as you can see, that is the correct definition. I'm not going to get too lost in the weeds on proofs. Y'all don't need to worry about it just yet. We're going to go over more of this next week. So there's a few different flavors of recursion as well. The most simple of which is going to be tail recursion, which the algorithm that we just looked at is an example of tail recursion, which is just essentially there's one recursive call and there's one base case. So you continue making the tail recursion call until you reach the base case, and then you return whatever the factorial function was trying to compute. Another example of recursion is binary recursion. So you can hypothetically make more than one recursive call in the same function. So in this case, this algorithm right here is calculating the Fibonacci sequence to the order of k. So you get the kth term in the Fibonacci sequence by returning the previous term plus the previous term. And I assume that y'all are familiar with the Fibonacci sequence being like 1, 1, 2, 3, 5, 8, 13, so on and so forth. If we wanted Fibonacci number k, let's say it's 6, the sixth Fibonacci number is 13, and that would be equivalent to saying the fifth Fibonacci number plus the fourth Fibonacci number should be 8 plus 5. What do you know? That's correct. So again, this is just like a brief little introduction to recursion. It's a topic that's going to come up in several different places. I think y'all are going to need to know the Fibonacci sequence at some point. I think I've seen it on a test before. Again, I think next week we're going to talk more about time complexity. The time complexity of this algorithm right here is O of 2 to the power of n. So not great time complexity, but it does give you the correct answer. And then the last thing on these slides is it's a game, it's a little math game called the Tower of Hanoi. Essentially, this is a little recursive algorithm that solves it for you. Y'all are interested. It's like this little game where you have three pedestals and you try to rebuild this tower on the pedestal that's all the way on the right. And the rules are you can never put a bigger disk on top of a smaller disk. As you can see, when the number of disks is equal to 3, the fastest solution possible takes 2 to the n minus 1 moves. You know, here n is 3. You can see the best solution is 8 minus 1 moves. I'm not going to explain this, but if y'all want, I think Cool Math Games has a place where you can practice this. So that's about it for today. If y'all have any questions, go ahead and ask them now. I think, you know, it's pretty straightforward stuff. We're going to be going more into detail on some of these topics later in weekend reviews, because I think to really understand like postfix and infix, you need recursion and you need trees. We're kind of just getting started with recursion, so I don't know. Any questions? Someone asked, is there a way that we can get access to these slides? Yeah, I can. Give me 1 second. I'll paste it in the. I'll paste it. Okay. Is that good? Y'all can access?